So depending on how I do all of the like title and thumbnails for this video, this is probably going to be the most inflammatory title and thumbnail that I've ever made. But let's just be clear about a few things. One, I am going to nitpick at Grant in this video, or the creator of 3B1B's. Two, this number is here for a reason. The videos that Grant makes are wonderful and amazing, and I enjoy them. You probably already know about them because this number is massive and it's math, so like... Anyway, and three, I really like this video. This video that I'm going to nitpick. I think it's a really good video. I think that in order to have a good foundation for talking about the things I'm going to talk about in this video, you should watch this video first. So if you have not done that, I encourage you to do that. So what am I going to talk about? Well, 3B1B's put out a video a few days ago that was a remake of a video that came out a while ago that talks about the Moser circle problem, and it's about just cutting a circle into regions, essentially. Again, if you have not seen this video, you should 100% go watch it. It's very good. There's a thing that Grant says in the explanation of that video that I want to nitpick, because if I nitpick at it, I can take this problem that has this type of math in it that you may enjoy, and I can introduce you to a whole field of math that does stuff with similar problems to that type of math. Okay? So this is what Grant says.
So yes, it does depend, but we're going to consider the cases where you never have any three lines intersecting with each other. This would be the generic.
And if you think too hard about it, like most graduate level mathematicians do, the thing that he says is false for the number of points on the edge of the circle being greater than 3. Because whenever you have more than 3 points on the edge of the circle, at each of those points, you're going to have 3 or more lines intersecting. And if you're focused on, well, he said 3 lines intersecting, well, then you have multiple subsets of 3 lines intersecting at those points on the boundary of the circle. And so in the construction of the Moser circle problem, this is what he means, what he says. He's totally fine. Everything's good for the most part. And it's more of like a, you do this step first and then you do this step next sort of thing. But if you take those two things and you didn't express them in that serial construction manner, you have a problem, right? You need there not to be these intersections of these 3 lines on the boundary of the circle. And so this is where we get to the idea of, okay, if we nitpick at that detail, what happens? So what happens if you actually force that when you're cutting up the circle, that no 3 lines intersect at a single point? So to make this alteration make sense for our context, what we're going to do is we're going to have our rules, right? Which the first one of which is just the one that we're nitpicking at, which is that any 3 lines cannot intersect at a single point. And the second one, to make this still sort of like a circle cutting problem, is that whenever we add a new line, we want to make sure that that new line intersects all of the previously drawn lines. Well, what happens? Well, gone ahead and drawn the picture, hopefully to just mark out which regions have been cut up in an instructive way. And if you look at that for a little bit too long, you notice that what happens is that you get the number of the regions from before plus the number of lines that you have in the particular case. And so the recursion that you're going to have here, where the number of regions is described by this function f of n, is going to be equal to n plus f of n minus 1 for all n greater than 0. And when n is equal to 0, you just get f of 0 is equal to 1. In the 3B1B's video, Grant connects this to Pascal's triangle in a particular way by talking about binomial coefficients and all of that stuff. And you can do a similar thing with this recursion formula, right? So if you want to derive the closed form, you can go ahead and look at the nth input to the function, expand that all out, and change the 0 term to just the 1, and you get 1 plus the nth triangular number. Or, in other words, n times n plus 1 divided by 2 plus 1. Now, n times n plus 1 divided by 2 is just n plus 1 choose 2. And then using that exercise from the 3B1B's video, you can go ahead and derive that n plus 1 choose 2 plus 1 is equal to n choose 0, which is just the 1, plus n choose 1 plus n choose 2, which comes, and that second sum comes from the exercise in that video. So the pattern that's found here is a little bit different than what's in the 3 blue 1 brown video. It still has this connection to the to Pascal's triangle via sums of binomial coefficients and all that good stuff. And actually, if you go to the Wikipedia page for this problem, which is called the lazy caterer problem, or at least the one that I've described to you right now is called the lazy caterer problem, and I will get to a whole field of math in here in a second. You get this diagram of sums of binomial coefficients from Pascal's triangle, and then you see the lazy caterer problem on there, and you also see the Moser circle problem. So these two problems are related in some way, at least by how they relate to Pascal's triangle, but they're also related in another way. And so the question I want to answer is like, well, why is this a good place to do more math or to start thinking about a whole field of math instead of what was done with the Moser circle problem? So if we return to our 4 lines case and we go ahead and number those regions just so that we have 11 of them again, what you can notice is that if I just remove the bounding circle and I count regions in the plane instead of just regions inside the circle, I end up getting the same number of regions. So the circle was just extra information. I didn't really need that to do this problem. And so this problem becomes a story about how lines cut up the plane. Note that lines are one less dimensional than the plane. The whole being one dimension less thing is the intuition behind what a hyperplane is. So given a vector space V, a subspace W, which is a subset of V, where the codimension of W is equal to 1 is called a hyperplane. And then I don't write this on the board, but an affine hyperplane is just some translation of a subspace, which is a hyperplane. And so usually when we're talking about hyperplanes in this context of, well, how do these hyperplanes cut up the plane, we're not talking about hyperplanes alone. We're talking about these affine ones, where you take a hyperplane and you move it around to cut up your one-dimensional higher space. And so when you have a collection of these hyperplanes, that's called a hyperplane arrangement. The problems that we've been talking about so far are those that have general position. In the 3 blue 1 brown video, Grant calls this generic position, which is sort of right. So I'm not going to get into how you specifically get at Moser's circle problem from this hyperplane arrangement point of view, because that takes a bit of time and a little bit more projective geometry than I am willing or prepared to talk about in this video. So that aside, what happens with hyperplane arrangements that are in what we call general position is that there's 2 rules, right? So one is that whenever you intersect P hyperplanes, and P is less than the dimension. So when P is less than the dimension of the parent vector space that these affine hyperplanes live in, the dimension of the intersection of all of those hyperplanes should be the dimension of the space minus P. Similarly, if you have more than the dimension of the vector space number of hyperplanes and you intersect all of those together, you should get the empty set. And so the study of hyperplane arrangements, they don't necessarily have to be in general position, but this study of hyperplane arrangements is this thing that's it's its own field of math. There's a book that I'll link it in the description that gives you an introduction to hyperplane arrangements or whatever. I don't remember what it's called, but it's a book that's just on hyperplane arrangements. People write papers about this thing till this day. And it's very general, right? I don't need to live in the plane to do this. I just need to live in a vector space. And most of the time that vector space is going to be finite dimensional. But sometimes you can't even visualize finite dimensional vector spaces. So if I replaced the real numbers with the complex numbers and I go to the C2, right? I can't visualize that thing. And in some sense, when you think about the complex numbers as a plane, that's wrong intuition here as well, even though that's what we tell you to do throughout grade school / college / high school. Or I guess grade school / high school / undergrad. we tell you to think about the complex numbers as like, well, there's a real axis and there's imaginary axis, and you do that even when you take graduate classes in complex analysis. You still sort of like have that intuition that there's this coordinate system. But sometimes that's not good intuition for what you're doing with the complex numbers. Okay, the point of that rambling was that sometimes you can't visualize what's going on. And so we want to go ahead and, we want to be able to like write these things down without having to draw a picture all the time, because also drawing in 3 dimensions is hard anyway. And 2, we want to be able to like think about the things in a relatively structured manner. And this is the idea behind defining polynomials. So let's just look at a really elementary example of a hyperplane arrangement. And that would be the Boolean arrangement in R2. So the reason I'm using the Boolean arrangement in R2 is because I don't want to do anything super difficult, but I also want to have a visual so that I can translate away from visuals forever, essentially. Not really. I'm going to give you another visual in like 5 minutes. But when you go ahead and look at the Boolean arrangement in R2, what that is that it's just where each of the coordinates is equal to 0. That's what the hyperplanes are given by. So you have the x-axis and the y-axis, and those are your 2 lines that cut up the plane, and they intersect at the origin. Great. Cool. We basically know how this thing works because you have, every time you've looked at a 2-dimensional graph, you have looked at this thing. You know there are 4 quadrants. Cool. You figured out the number of regions. You sort of understand the Boolean arrangement, but not really. Your first hyperplane, which is just the x-axis, has an associated linear form. If you're thinking about horizontal lines in the plane, the horizontal line that corresponds to the x-axis is just y is equal to 0. So the linear form associated with the x-axis is just y. And then for the second hyperplane, again, which is similarly just the y-axis, now you're just flipping all of the letters around, right? Your associated hyperplane is the line x is equal to 0, or that's the line that corresponds to the y-axis. And so your corresponding linear form is just x. And so then we would say that the defining polynomial of the Boolean arrangement in R2, and you could do C2 here, it's just I wanted to draw the picture on the board for this particular example, is then just Q sub this fancy A is equal to xy. So in general, the defining polynomial is then just given by the product of linear forms that are associated to hyperplanes that are in your hyperplane arrangement. And this is helpful because it lets you write down an arrangement without drawing a picture, right? So for example, there's this arrangement called the braid arrangement. If we look at it in R3, then it can be expressed by the defining polynomial x1 minus x2 times x1 minus x3 times x2 minus x3. And then if you were to say you want to look at the Boolean arrangement, but instead of in R2 or C2, you want to do it in Rn or Cn, then you can go ahead and write down the defining polynomial that is just the product of the different monomial coordinates, or the dual basis coordinates if you want to be fancy about it. So it's just x1 times x2 times x3 times x4 all the way up to xn for whatever dimension n that you're thinking about with that particular instance of the Boolean arrangement. So in general, how we get the hyperplane out from a linear form is we take the set of all the vectors in the vector space such that the linear form evaluates to 0 at those vectors. And again, just to say it one more time, your defining polynomial is just the product of these linear forms that define these hyperplanes. Okay, so we have a way of writing down these non-visual things, potentially non-visual things. And going back to the 3 blue 1 brown video, the main crux in the argument of being able to count things was keeping track of intersections. And there's also a way to keep track of intersections when you're working with one of these hyperplane arrangements that you can't necessarily visualize in the standard Euclidean geometry way. So I want to just end this video by giving you a tool or a visual tool for how one may want to visualize what's happening intersection-wise with a particular hyperplane arrangement. And so this is going to keep track of that same intersection information that Grant had in his really nice diagram, which I'll put up on screen right here near the end of the video, where he was keeping track of all of those intersections between lines in that graph that he was focused on. Well, here we're going to develop a similar combinatorial object, but it's not going to just have lines and points and information in it. It's going to have a little bit more information. So if I go ahead and give you a hyperplane arrangement, fancy A, which is just some collection of hyperplanes, H1 through HP, or however many hyperplanes that you want, it has an associated defining polynomial, which is given by the product of the linear forms which define those particular hyperplanes. Okay, well, how are the hyperplanes defined? If you think about them as sets, they're just a set of vectors where the linear form is equal to 0. So if I have a hyperplane H, and I have a vector V that makes the linear form of H0, then that vector V is within the hyperplane H. So if I instead take two hyperplanes, H and K, and I find a vector that makes the linear form for H equal to 0 and the linear form for K equal to 0, then my vector is going to fall into both H and K, which by definition means that that vector falls in the intersection of those two hyperplanes. So to build this alternative visualization for hyperplane arrangements, I want to look at a very, very simple example, which is still non-trivial in terms of its ability to visualize things, right? So we looked at the Boolean arrangement in R2 already, which is when you have x times y as your defining polynomial, or the lines x equals 0 and y equals 0. Now I want to bump that up to R4 or C4. Depends on how spicy you're feeling. It doesn't really matter. It doesn't change the visual object that I'm about to present to you. So your defining polynomial here is q sub fancy a is equal to x1, x2, x3, x4, or x, y, z, w if you want to use those letters. But for me, I'm just going to use x1, x2, x3, x4. And our hyperplanes are x1 equals 0, x2 equals 0, x3 equals 0, and x4 equals 0. At the bottom of this lattice that I'm going to build to visualize what's happening with the intersections in this hyperplane arrangement is I'm going to have just the vector space itself. All right. And on the next level up, I'm going to have the hyperplanes themselves, right? And you can think about this as all of the hyperplanes are connected to the vector space itself because all of the hyperplanes live inside of the vector space that you're working in. Once I have all of those things written down, I'm going to move up another level, and I'm going to have intersections of hyperplanes that are in this case, it's just two hyperplanes intersecting, but I'll get into what's actually happening in a second. So you have two hyperplanes intersecting, and I want to keep track of where those things live inside of, right? So x1 equal to 0 and x2 is equal to 0 is the intersection of the x1 hyperplane and the x2 hyperplane. And so that will be connected down to x1 equals 0 and x2 equals 0. Similarly, the x2 equals 0, x4 equals 0 intersection of the x2 hyperplane and the x4 hyperplane will be connected down to the x2 and the x2 equals 0 node and the x4 equals 0 node. And we sort of continue this up. So the next row will be three hyperplanes intersecting. And then at the top, we're going to have all of the hyperplanes intersecting, which in the case of the Boolean arrangement ends at the origin, similar to what happened in the R2 case that we could visualize with Euclidean geometry. So just to note what's actually happening here for when you do, if you decide to do this with a general hyperplane arrangement, is we're actually keeping track of codimension, or how far off you are from the original vector space in terms of size, right? So at the bottom of the lattice, we have codimension 0 or dimension 4, because that's just the dimension of the vector space. And then when we move up, we have hyperplanes here, so our codimension is 1, or our dimension is 3 in this case. And then when you move up another level, we're not looking at the intersection of two hyperplanes. What we're really looking at is we're looking at all of the intersections that result in codimension 2 subspaces, or in this case, dimension 2 subspaces. And then again, when you move up, we're not looking at the intersection of three hyperplanes. Instead, what we're looking at is we're looking at all of the codimension 3 subspaces that result from intersecting hyperplanes. And then lastly, at the top, we have all of the code dimension for subspaces, which there is only one that results in intersecting hyperplanes. So what's really cool about this lattice is that this describes all of the intersection information about the given hyperplane arrangement. And you can always make one of these that records all of this intersection information, which was core to answering the question that came up in the 3B1B video, right? And so the question here that people still study and is fairly well studied for certain particular arrangements is, well, how do you get geometric information out of this combinatorial object, right? So much like how there was a graph in the 3B1B video, that graph is a combinatorial thing, and it's being used to describe geometric information that's happening within this vector space. Or within, in the case of the 3B1B video, the circle. And so, yeah, that's like a pretty good place to stop this video, because I don't want to go too far down the rabbit hole. But if you enjoyed the 3B1B video, you should also just, pick some lines, make a lattice, and see if you can figure out some patterns. Again, this is pretty well studied. I've linked to an introductory book around this stuff below, and it does sort of talk about projectivization in there too, so it kind of gives you a starting point to connect this to the Moser circle problem if you would like to. But I kind of just did it with a little bit of nitpicking because I was given an avenue and I took it. Because I've kind of wanted to talk about these things since I learned about them this past semester, because it was a very cool class. It was very fun, and just like there's a lot of connections here. There's a lot of algebra stuff that's happening. There's a lot of geometry stuff. There's a lot of topology stuff. There's a lot of stuff that's all interconnected here, even though it doesn't seem like it should be. And that's the type of math that people like, at least when you get high enough in math. A lot of people like things that are very unexpectedly interconnected. So that's it. Again, I did like this video. I wanted to use it as a vehicle to talk about hyperplane arrangements and introduce people to a wider field of math that is similar to the math that's talked about in this video. So again, if you liked the math in this video and you liked thinking about what's happening in the video you just watched, if you got it this far, then you should check out that book. Anyway, that's basically it. If you enjoyed this video, give it a thumbs up and subscribe for more math stuff. As always, I am Nathan. This one was Chalk, and I will see you next time.